everyone. Thank you so much for being here with me today. My name is Anna and I'm part of business development team here at Geo-Modeling, and welcome to our last webinar of 2025. We're truly excited to close out this year with you and reconnect in 2026 as we have several updates and new developments planned that we're excited to share with you next year. So please follow our YouTube page, our LinkedIn page, just to stay informed what's going on and what's coming next. So today we're diving into geo-modeling challenges and exploring why scale plays such a critical role. Most of us first encountered the concept of scale probably in school, where it was defined as the relationship between measurements on a map and those in the real world. And in the context of cartography, it works also well. However, when we move into subsurface investigations, geological 3D modeling, uncertainty analysis, and mineral resource estimation, scale becomes much broader and more nuanced concept, and it directly influences how we interpret data, build models, and assess confidence in our results. But before we get started, for those of you who just joined us, who had never been in our previous webinars, I just want to briefly introduce K-Mine. We were founded in 1994 and grown our presence across Europe, United States, and Canada. And we have a team that includes software engineers, geologists, mining engineers, including specialists that are certified under NF 43101 and JORC standards. So we work with a broad range of clients that includes early exploration teams and large companies, but our focus is always delivering reliable, cost-effective solutions that are tailored to the specific needs of each project. So what we do in Geo-Mine, we develop software that is built specifically for mining industry, supporting the entire workflow from exploration right through to production. And our platform offers flexible models both for open pit and underground operations. One of our key strengths is adaptability, so you can start with a single model and scale up to the full suite depending on your project needs. Speaking of scale, right? So our tools are designed to help you manage geological data more efficiently and develop mine design plans and optimize plans for short and long-term planning. So if you decide to integrate also IT or dispatch systems, you can also enable a real-time monitoring just to keep operations running smoothly and well-coordinated. Our software, though, grounded in real-world industry experiences and challenges that we encountered through our consulting work. As I mentioned, we have specialists that includes qualified persons who prepare technical reports in line with NI 43101, SKF 1300, JORC standards, and across multiple project stages like preliminary economic assessment, pre-feasibility, feasibility study, mineral resource estimation, and others. So we work across a broad range of hard rock commodities with a particular focus on critical minerals. If you'd like to learn more how we can support your project, please feel free to leave a comment or reach out to us through the contact form on our website. So today, we talk about how scale shapes the way we interpret and work with geological data and why it's such a critical factor in geomodeling. We'll look at the balance between detail and regional coverage. We'll share best practices for handling scale in numerical models, and we'll discuss how scale-related issues can affect uncertainty and risk. We'll also walk through real-world examples of scaling errors and finish up with practical tools and workflows that can actually help you to make the process more efficient. So let's revisit some of the core definitions of scale. As I mentioned, scale is defined as a relationship between a distance measured on a map and the corresponding distance on the surface the map represents. In cartography, scale is typically shown in three ways. The first is verbal or written scale. For example, 1 centimeters equals 250 kilometers. This means that literally 1 centimeter on the map represents 250 kilometers on the ground, and it's usually the easiest type of scale to understand because it uses familiar units. Second type is graphic or bar scale. This is the visual scale bar you often see on the maps. Bar scales are specifically important because they adjust automatically when a map is resized. And the third type is the representative fraction, or RF. This is sometimes called the natural scale, for example, 1 to million. This means that 1 unit on the map equals 1 million on the same units on the ground. So on a well-prepared map, you'll typically see both types included to ensure accuracy and clarity. Scale is also what we use to classify maps from overview and regional maps to more detailed ones. It directly determines the level of accuracy in the information being represented. This can range from mega regions shown at small scales to local sites and individual drill collars at large scales. Beyond mapping, scale also plays a supporting role in defining the stage of geological knowledge and investigation. And if we look at industry guidelines and regulatory frameworks across different countries, we see that scale requirements vary not only by jurisdiction, but also by stage of work. In general, most frameworks recognize 3 to 4 stages of geological investigation, again, depending on the country, depending on the region. This typically progress from reconnaissance and prospecting through general exploration to detailed exploration, and each stage produces resource data with a clearly defined level of geological confidence. On the slide, you see an indicative set of studies typically carried out at each stage of geological investigation. You can also see examples of the scale used at those stages. So we usually start with the reconnaissance stage, often referred as G4. This involves broad regional level studies based mainly on public data, and it includes regional geological mapping, remote sensing, and aeromagnetic surveys. These activities aim to identify favorable settings and highlight greenfield areas. The next stage is prospecting, or G3. This stage focuses on fieldwork and ground truthing. This includes more detailed geological mapping and geochemical sampling. Geophysical surveys and sampling are used to identify mineral occurrences and secure claims. And that's followed by general exploration, or G2. At this stage, the work becomes more targeted and detailed. Surveys are usually used to define the size, geometry, and potential of mineralized zones. So this often supported by shallow drilling and initial core sampling. Finally, we move into detailed exploration, or G1. This is where intensive drilling is carried out. So the goal is to build robust 3D models, estimate resources, and assess economic viability. So speaking of difference between different countries in terms of the definitions and the usage of scale, if we talk about, for example, post-Soviet countries, the stages of geological investigation are typically organized into 3 stages, and that includes regional studies, prospecting and evaluation, and detailed exploration. So these stages follow a strict sequence, moving from broad, generalized work towards increasingly detailed investigations. This progression includes small-scale mapping and airborne surveys, advancing to drilling and seismic surveys and sampling. The scale of work moves from regional coverage down to specific sites with the goal of preparing deposits for development. The first phase is regional investigation and forecasting. At this stage, the focus is on building a regional geological framework and identifying prospective zones. This is typically done using small-scale mapping, airborne geophysics, seismic surveys, and parametric drilling. These activities lead to the definition of forecast resources. Maps at this stage are small scale, typically ranging from 1 to 200,000 to 1 to million or smaller. The second phase covers prospecting and evaluation. During prospecting, work becomes more focused and detailed. This includes site preparation, structural mapping, detailed seismic surveys, drilling, and sampling. And this is followed by the evaluation stage, where resources and reserves are estimated. Preliminary geological and economical assessments are also being completed, and mapping scales here are medium to large, generally between 1 to 50,000 to 1 to 200,000. And the final phase is exploration and development. This includes detailed deposit exploration, where mineralization is delineated and the reserves are calculated. It also includes mine site exploration during production, focused on extending known mineralization. And at this stage, large-scale maps are used typically from 1 to 10,000 to 1 to 50,000 or larger. Overall, as projects move from regional studies to detailed exploration, mapping scale decreases, and at the same time, detail and confidence in geological information increase. By the way, the word scale itself is rarely mentioned explicitly in national reporting codes within the CRISCO family. However, these codes implicitly assume that the competent person has reviewed all of the previous work completed on the project. They also assume a consideration of geological information produced at different scales of investigation. In other words, when mineral resource estimates are justified, they are expected to be supported by data from multiple geological scales. For example, in Section 2, Management and Execution of the Seam Mineral Exploration Best Practices Guideline, we find the following guidance. The geoscientist is expected to base an exploration program on a solid understanding of regional scale geology. This also includes property scale geology, the target commodity, and the style of mineralization. That understanding should be supported by the field data and a thorough review of published corporate and private information. And based on this, the exploration program should be designed to test interpretation credibility. A similar expectation is clearly stated in NI 43-101. Here it says that the technical report must be illustrated by legible maps, plans, and sections. All must be prepared at appropriate scale to distinguish important features. Maps must be dated and include a legend, author, and source, scale bar or grid, and north arrow. And all reports must include a location map and completion map outlining the general geology of the property, end of quote. But in practice, we still occasionally see technical reports where these basic requirements for presenting exploration results are not fully met. And this can lead to misunderstandings on the investor side and ultimately to incorrect interpretations of mineral resource potential. We sometimes receive multiple requests from junior companies planning further exploration or even moving towards production, but with a very limited baseline data. In some cases, there is no topography or no drill hole data at all. And the only available information might be geophysics or few surface samples, for example, and yet the client is already considering resource estimation, the start of mining activities. The situation is particularly common in weak regulatory environments. When it comes to reporting exploration results, we often see two extremes. The first one is when the scale and location of mineralized zones are unclear and maps may be missing a coordinate grid, drill color collocations, sample points, or even a north arrow. And this makes it difficult to understand the spatial context of the data. The second extreme occurs when at very early stage reports already present tonnage and grades by resource category. However, if we look at JOR code, it clearly defines how information should be reported at this stage. Any such information related to an exploration target must be expressed so that it cannot be misrepresented or misconstrued as an estimate of a mineral resource or reserve. Exploration results include data and information generated by mineral exploration programs that may be of use to investors, but which do not form part of resource declaration, end of quote. And also there can be the opposite situation. Sometimes a very detailed large-scale information exists for a permit area supported by a dense exploration grid. For example, multiple veins may already be identified, but at the same time, there might be a little understanding of regional settings or controlling structures or secondary mineralization processes. In cases like this, effective follow-up exploration requires integration of all available regional information. And this includes nearby prospects, analog deposits, and broader analysis of tectonic and structural controls. So when we talk about geological modeling and resource evaluation in these environments or through web-based technologies, a wide range of new capabilities has become available. This includes dynamic scaling, online geological maps from many countries, and access to registries, cadastral systems used to manage land tenure, protected areas, and other constraints. In GIS, dynamic scaling refers to the automatic adjustments of map elements as the user zooms in or out. This ensures information remains readable and relevant sometimes, and something that is not possible with static paper-based maps. Key aspects include scale bars or map sheets that automatically update units and lengths. They also include dynamic labeling and scale-dependent visibility of features. So as you zoom in, detail appear. As you zoom out, less critical information is hidden. And this prevents visual clutter while maintaining clarity and context at every scale. So speaking of GIS product, of course, we cannot not talk about KMI since we have our own software. And in this video, you can see how to automatically convert different coordinate systems and import imagery from Google Maps directly into KMI environment. All you really need to know is the coordinate system you're working in. You can select the boundary of your area of interest using the built-in geo-calculator, recalculate the coordinates of the boundary points, and then load the corresponding Google Maps tiles. You'll notice that the system includes a long list of coordinate systems. By entering the system ID into the filter, you can quickly find the one that you need. The world map below shows the boundary of the selected zones in white, and you can drag frequently used coordinate systems into your favorites for easy access. And if needed, you can also adjust map display and switch between satellite and road map views. Coordinates can be imported and exported in CSV and KML formats, which makes it easy to integrate external data into your workflow. And together, the coordinate conversion tools and Google Maps integration provide a powerful way to analyze project data. In fact, this functionality has helped us tremendously to avoid serious mistakes in resource estimation. It has even supported geologists and legal teams working at operating miles. For example, one time there was one case involving a titanium deposit. The mining license listed a large area and significant tonnage. However, when we analyzed the spatial data, we discovered that the part of the licensed area was covered by pine forest and lay within protective reserve, and mining permits for that zone were denied, which restricted development, required part of the resources to be excluded. So because this was identified early, the team was able to amend license in time and save substantial costs in future mineral use taxes. Similar situation actually occurred at one of the iron ore quarry. The long-term mine plan showed a pit outline extending to protected zones that included railway line, station, and regional gas pipeline. And these facilities were not reflected in the original layout as they lay beyond the short-term planning horizon. So we recommended contacting the railway authority to explore relocation options, but the request was denied, making it clear that the mine development strategy needed a fundamental revision. Another case involved Google Maps imagery at the graphite operation, and the satellite images revealed overlap with a cemetery, a sports stadium, and residential housing. So addressing these constraints would have required major investments, including, let's say, water management, housing compensation, cemetery relocation. So when all of these factors were included, the project actually was found unviable. So we've encountered many situations like this in our practice, and that's why the value of integrated Google Maps tools with dynamic scaling and coordinate conversion is very clear. They help identify special constraints early, reduce risk, and support more realistic and defensible project decisions. Although scale and resolution are different concepts in GIS, they are closely related and often discussed together. Scale primarily describes how real-world distances are represented on the map, while resolution defines the smallest object that can be distinguished. The Spatial resolution refers to the level of detail in an image expressed through pixel size. Higher spatial resolution means smaller pixels and more detail, while lower spatial resolution results in larger pixels and less detail. And overall spatial resolution determines visual quality and how clearly individual features can be identified. As grid cells become smaller, the image captures finer details, which can be critical for accurate interpretation and analysis. But when it comes to raster data, resolution directly limits the level of detail you can see at a given scale. Even a very highly resolution imagery can lose much of its value at smaller scales because fine details are no longer visible. For vector data, such as topographic maps, scale plays a much bigger role in how much detail is shown, while resolution is less limiting. In GIS, raster data is represented as grids of pixels and is commonly used for continuous variables like satellite imagery, elevation models, temperature, or terrain. Vector data, on the other hand, is built from coordinate defining points, lines, and polygons such as like roads, boundaries, and drill locations. Vector data offers high precision, good scalability, and rich attribute information, although it can result in larger file sizes. Raster data is ideal for things like surface analysis, but can be pixelated. Vector data, on the other hand, is better suited for the precise mapping, network analysis, and editing. But in practice, both types are often used together to support comprehensive spatial analysis. Ultimately, spatial scale has a fundamental impact on geological modeling. It influences data resolution, the geological pattern we can identify, and model accuracy. Finer scales allow us to capture local heterogeneity, such as karst features, and broader scales highlight regional trends and structural controls. In numeral geology, scale and resolution play different but closely connected role. Scale, whether we're looking at the crust, reservoir, or an outcrop, defines a physical extent of the system we're modeling. Resolution, on the other hand, controls how finely geological features such as faults, faces, fractures are represented, typically through grid size or model detail. High resolution allows us to capture geological heterogeneity, like thin layers or subtle structural features, which can be critical for understanding fluid flow or reservoir behavior. At the same time, higher resolution comes with a significant computational cost. That's why upscaling is often necessary, moving from very detailed models to coarser, more manageable ones that are still practical for large-scale simulations, resource management, or hazard assessment. This graph illustrates how scale varies across geoscientific and engineering applications. The dataset spans an enormous range from measurement on the other order of tens of thousands of feet down to micrometers. On the far left, the seismic stack operates at the largest scale, and at this level, certain types of variations such as fine vertical detail are necessarily averaged out. Moving to a smaller scale, the well log shown next is able to capture these vertical variations because it operates at much finer resolution. Going even further, thin sections reveal details within individual strata that are only visible at this very fine scale. Each dataset adds a different layer of understanding, but only within its own scale window. And the same principle applies to geophysical data interpretation. Scale and context must always be considered. This means understanding the spatial and temporal limits of each dataset and relating them to geological processes and models we're trying to interpret. For example, seismic data can vary widely in resolution and frequency depending on wave velocity and wavelength. Gravity and magnetic data have different sensitivities and level of ambiguity depending on the distance and orientation of the sources. Electrical and electromagnetic methods differ in penetration depths and complexity based on subsurface resistivity and conductivity. Because of this, it's essential to match scale with the right interpretation tools and techniques, and when scale, resolution, and method are properly aligned, the results are far more reliable and meaningful. Data types reveal different aspects of geology depending on the scale at which they are collected. At the core scale, measured in millimeters to centimeters, core scale features such as veins, sulfide textures, alteration boundaries, and microstructures can be identified. At the sample scale, typically ranging from centimeters to meters, sample scale observations focus on assay intervals, grade variability, and lithological context. So when we move to the geophysical scale on the order of tens to hundreds of meters, geophysical scale data reveals much larger features. This includes major structures and broader trends in conductivity and density. And because each dataset has its own inherent resolution, we are able to observe it as always controlled by scale. Fine scale features may disappear at larger scales, even though they can be critical for understanding ore continuity and mineralization behavior. So resolution and grid cell size are critically important when it comes to 3D geological modeling. In vein modeling, scale refers to how vein dimensions such as length and thickness change across different observation levels, from outcrop to mine scale to regional scale. And it also reflects how modeling software handles scale, different data types like drill hole samples and modeling parameters such as triangle size or snap intolerance. All of these influences model realism, from small mineralized shoots to large structural systems. So in practice, this means managing multi-scale detail from broad fault system down to individual ore shoots while maintaining consistency in geometry and grade distribution. In K-Mine, vein models are built using drill hole data, surface information, and structural controls such as fault surfaces. This allows us to bridge scales, linking discrete point data and continuous geological surfaces. In implicit vein modeling, scale becomes essentially important. Narrow veins represent a small-scale challenge, while large faults operate at a large scale. Mathematical interpolation methods such as radial basis functions or kriging define veins as isosurfaces, while structural data constrains geometry. Often, the most realistic results come from hybrid methods combining implicit and explicit modeling. And it's also important to note that continuity is highly scale dependent. At a large scale, structural continuity may extend for kilometers. Within that structure, vein continuity may persist only for tens of meters. So because gold is often concentrated in narrow veins, great continuity can appear low globally but strong locally. And for this reason, continuity should be discussed at multiple scales. When we move into mineral resource estimation, scale again plays a defining role. The scoping study is generally based on inferred resource with wide drill spacing and global continuity assessment. A pre-feasibility study requires a higher confidence supported by closer drill spacing and indicated to measured resources. At this stage, continuity can be assessed at a local scale, while inferred resources are excluded from economics. By the feasibility stage, modeling reaches maximum detail. Scale-related challenges often stem from choosing the wrong level of detail. Using mismatched data scales leads to misinterpretation. There's always a detailed trade-off between resolution and coverage. Scale-related errors directly affect model reliability and risk, and integrating data across multiple scales remains a key challenge. High-resolution data increases cost, often with diminishing returns. Project teams must balance technical details with practical constraint. And modern software like K-Mine supports scale decisions, balancing resolution, coverage, and reliability. And that's it for today. Thank you so much again for being with us in 2025. Merry Christmas, everyone, and I'll see you in 2026.